Okay, class. Here we are one more time, and we're going to pick up on the air control presentation. We've got a few minutes, 4 or 5 slides, I don't know, maybe a little more on this one, and then we're going to move on to our next topic, which will be about sizing control valves for HVAC systems. So a little bit of backtracking here. We have done this slide before, but I thought it would be good to go back and start here. And you can see in the glass, it was filled with cold water out of a water fountain and allowed to heat up. And as it heats up, the water cannot hold as much oxygen or nitrogen. Probably those would be the two primary gases, maybe a little argon, but maybe that's one bubble out of the glass. And so as it continues to heat up, these gases will come out of solution and just be vented from the top of the cup. And so this air has got to be handled. Even in a chill water system, changing temperature from 40 to 55 or 60 degrees is enough that you're going to generate air and it have to be controlled. We went through this discussion with the bends and the deep sea diver in class. Basically, the body uses the oxygen and the nitrogen for divers that go down in pressure is driven into the blood. And then if they come up too quickly, it comes out, causing it to bubble. And this has all sorts of causes all sorts of problems for divers and results in the bends. So under air separation, the point where the compression tanks connects to the system is the point of no pressure change, regardless of pump operation. So at that point, turn the pump on, turn the pump off, and there is no pressure change. The only way we change that pressure is by adding water to the system or heating up the system or cooling it down, which causes a change in the volume of the system, which is essentially the same thing as adding or taking water away. It's also the point of separation of free air from the system. So we want any air bubbles to go into an air separator there, and so they can be vented to the compression tank or in an oxygen-free system to the air vent, automatic air vent, and be purged from the system. Effective air control design then takes account these conditions that affect the release and absorption of water in the air, and that is if we increase temperature, we decrease the amount of nitrogen or oxygen that the water can hold. If we decrease pressure, then the nitrogen, oxygen will come out of solution. So we get rid of air in a system by increasing temperature and decreasing pressure. Air is roughly 20% oxygen, 70% is actually 21%, 79%, but at this level of analysis, we can use 20 and 80% just fine. Air within the closed system quickly loses the oxygen via corrosion or oxidation. So long as we're not continually putting water in the system, then the oxygen will go away very quickly, and then the corrosion will stop. So it's not a problem. And then of course, if we're continually adding fresh water to the system, then if we're adding fresh water, we can have a steady supply of oxygen. But if we're not, then the gas dissolved is going to be almost entirely nitrogen. These are curves that show the solubility of nitrogen. It's expressed in terms of water volume, if allowed to, if separated and allowed to expand to 0 pressure and 32 degrees Fahrenheit. So I'm trying to get my pointer. There we go, finally. So that's on the y-axis. On the x-axis is just temperature. And then all these curves are for different pressures. And so you can see, pick a temperature, pick 100 degrees Fahrenheit. And we see as we lower pressure, this is not much oxygen at all. What is that? 1, 2, that's a little over what's that, 1.2%, something like that. If we go up to 10 psi, that goes up to over 2%. If we go up to 150 psi, that goes up, what is that, 15, 14, 13.6, 13.7%. So these curves are useful, and you should look at them to the point that you understand what's being described, the physical processes involved here. So if we pick a temperature and decrease pressure, the oxygen or the nitrogen, the gases come out of solution. If we pick a pressure and we decrease temperature, say pick 75, if it's really cold, we can hold, 13+%. If we heat that up to 250, it falls to a little bit above 4%. Okay, so this slide just describes some of the data. I think what we've already been through here, so I'll let you look at that. Effective air control means designing a system so that when nitrogen is released from solution, either by heating or pressure reduction, it will be primarily, you can't necessarily make it all at one point, but primarily at one point. And that should be the point where the air separator is located that feeds into the compression tank. We must have adequate system pressurization because areas of low pressure will allow nitrogen to release from the solution. So this involves the operation of the pump and trying to design this so that the air is going to come out of solution at a control point where we can collect it. So this means locating all pumps in the system with respect to the point of no pressure change so that their operating pressures are always added to the pressures existing at each point in the system. So that means putting this compression tank hopefully right at the suction of the pump. Pump should not be a cause of creating reduced pressure areas at remote points in the system where air can be released. So this would be if we put the compression tank connection on the discharge side of the pump. Ideally, air control is complete when the air separator can be located at a single point, which is the area of highest temperature and lowest pressure. That would be nice if we could do that, but unfortunately, sometimes we can't make it happen at both of those. So this is seldom possible. So the engineer must provide not only effective separation equipment, but design the piping circuitry so that any free air within the system will be carried back to the point where it can be separated and directed into the compression tank or the air eliminator. So this is important, this point. Normally a velocity of 2 feet per second is adequate to prevent free entrained air from forming air pockets. So if we keep our velocity, especially in downward pipes where the flow is going downward at 2 feet per second or above, it will pull the air with it back to the point of air separation. High points in various piping circuits can be collecting points for free air, such as coils or any piping or any reservoirs up on the higher levels of the system. Air is going to rise when the system is filled, and if we don't vent it, it will stay there. Proper pipe sizing, particularly in down feed return piping, is often effective at preventing air traps at high points. This means that we're going to have our 2 feet per second or higher in this down feed return piping, and that will bring air bubbles that have come out of solution back to the point of air separation. Best location for air separation equipment depends on the particular system. When possible, select the point where we have the highest temperature, lowest pressure. We've said that. When this is not possible, the point of highest temperature should receive first consideration. The point of highest temperature should receive first consideration as the best point for air separators, even though it is often located at the bottom of the system under full static pressure. So you have to look at it, but typically temperature takes precedence over pressure. Except possibly for high-rise buildings, air separation at points of elevated temperature is generally an effective way to deaerate a system. Further, since boilers are usually protected by pressure relief valves, air separation at or near the boiler supply then places the point of no pressure change near the pressure relief valve, which is another design point that we like. Okay, so this slide illustrates the requiring the velocity to be greater than 2 feet per second, especially in pipes where the flow is downward, in order to pull those air bubbles back to the point of separation. If we have less than a half foot per second, then the water can be flowing down, but the air bubbles will still rise, and you won't be able to control them and bring them back to a point where they can be controlled, removed, or eliminated. So that's what this slide is about. This is an important point, and you should memorize this 2 feet per second. Okay, boiler dip tubes. A very common and effective air separator is the conventional hot water heating boiler. Lots of buildings just, they call them boilers, but they don't boil, they just make hot water. They're just big commercial hot water heaters. And boilers, these types of boilers typically or often have large internal water passages, water velocity is low, free air is released in heating and can rise to a convenient point of collection. From this collection point, air can rise into the compression tank or be eliminated. To prevent free air from collecting at the top of the boiler and being circulated out in the system into the coils, which is what they mean by radiation, boiler dip tubes are used either on the top or the side, and some boiler manufacturers provide these as standard equipment. Basically, this dip tube sticks down into the system if on the top, or it can be installed on the side. There's different styles of them, and it allows the air bubbles to rise up, and they will go off through a separate pipe to the compression tank, and the water goes out to the system. So, different configurations, boiler dip tubes for top outlet boilers can look like this from system. You can have them styled like this, where the air stays in the boiler and is vented this way, or it can be handled all by the dip tube. On the side, it looks like this, and dip tubes for reverse flow boilers can look like this. But at any rate, that's an effective way to remove the air from the system. We also have IAF Air Separators, and what these do, these use a rotary type action where, I'm sorry, this is not the rotary separator. This just slows it down. If a boiler is not available as a point of air separation, another low velocity area must be provided. A low velocity air separating tank equipped with a dip tube to create a flow reversal can effectively be used. And again, this is the 6-inch or a ½ foot per second. So these things are just a large diameter. It slows the flow down and it allows the air to flow up to the top. And then it's a dip tube-like assembly to remove the air to the compression tank, and the water goes on off to the pump. So that's what's called, this is a Bell & Gossett IAF inline air separator. A straight through tank for air separation. Even though it slows, the flow is likely to pass some air, so these are not the best way to do it. The vertical distance the water must travel and its velocity are directly related to how much air will be separated. The IAF model with dip tube separator also serves as an effective settling point for sediment and debris. So particulates and a little bit of crud that flows in here, if the velocity is low enough through this thing, it can settle to the bottom, and then we can occasionally purge this thing and remove that. This is the rotary air separator, the Rolairtrol separator. These are better. They work better and can be smaller than the IAF separator. So what these things do, the inlet and outlet are tangential connections, and they cause the water to spin around in a centrifugal nature, and the air bubbles will, because they're less dense, they will go to the center of this thing where they can be removed. So it creates this vortex or whirlpool in the center where entrained air can collect and rise into the compression tank installed above. The action of centrifugal force sends the heavier air-free water to the outer portion of the tank, allowing lighter air-water mixture to move into the lower velocity center. Air collecting screen located at the vortex aids in developing a low velocity area at the center. So this is probably what most people use these days. Compression tank installation. As air bubbles are separated from the system, either a boiler dip tube or an air separator, they must be allowed to rise into the compression tank. As free air rises into the tank, an equal volume of water must be replaced and returned to the system. A piping connection, the piping connection to the air separation equipment and the compression tank must always pitch up and be large enough in diameter to allow the water and the air to pass each other at the same time. At least a 3/4 inch diameter pipe is needed. When horizontal piping must be used, we must increase the diameter of the pipe, and the next figure has recommended pipe sizes. So we can see that if we can pitch it up, you see total length of horizontal connection only, and you see the tank fitting, the 3/4 inch ATF and 1 inch ATF. And if you're going to manifold tanks together, here are some recommendations on pipe diameter. Airtrol tank fitting, if there is free communication between the compression tank and the circulating system, water, several bad things happen. I think we've already talked about this. Deaerated water can absorb nitrogen from the air in the compression tank, and we can get gravity circulation between the cold water in the compression tank and the hot system water. This is for a heating system primarily. Water in the compression tank can rise to close to the system temperature, requiring a larger compression tank to be used. Airtrol fittings are a B&G's product to reduce gravity circulation between the compression tank and the hot water system. This just shows a picture of the Airtrol tank fitting to prevent the gravity circulation. This is kind of our typical system picture. We've had that before. And questions. And at this point, since I can't hear you, I'm going to assume there's no questions. We can talk about any that you have when I get back to class. So I'm going to stop this now and go to our next presentation. Okay, class. So I will email a PDF file of this presentation to you when I send you the links to the YouTube videos. So this is basic system control and valve sizing procedures. Okay, so control of HVAC systems is obviously critical if we're going to maintain comfort conditions. Commercial buildings are usually sealed. Some will allow you to open windows, but generally speaking, the windows can't be opened. And we also use large amounts of glass in these buildings, at least in the lobby and some areas. Architects love to design monuments to themselves, and a major part of that is having these large expansive windows, and that makes control more difficult and makes heating and cooling loads spike more than they would otherwise with more typical construction. Okay, so HVAC capacity in general can be controlled from the water side or the air side or a combination. This presentation, we're going to talk about water side control. In the advent of variable frequency drives, it's possible to control it from one side or the other or both, but we have to start the discussion someplace, and we're going to deal here with water side control. The picture is of a primary secondary system with variable secondary flow with VFDs, and we have a presentation after this one that goes into primary secondary systems. So we're not really in a position to discuss this much at this time. Okay, design conditions. Design condition is used to connote the period of maximum system loading. So we have a design heating load and a design cooling load. Now, the actual design condition is pretty complicated to determine, and is dependent upon all of these variables. Where the building is, prevailing wind velocities, construction, occupancy, lighting, ventilation, a lot more. All that stuff we put in the carrier program. And so all HVAC engineers these days use a loads program, typically train trace or carrier HAP, in order to help them calculate and quantify these design conditions. And you usually want to be conservative, which means you want to perhaps overestimate the load a little bit, because you'd rather have a system that's 10% oversized than 10% undersized. People get pretty upset when they're not comfortable, when it's really, really hot or really, really cold. Actual design condition rarely, if ever, actually occurs, but it's still important in the design process. So even though the design condition may never occur, it's important because it serves as the basis for sizing all your system components: boilers, chillers, terminal units, air handlers, coils, pumps, valves, piping are all sized on the basis of the design load. The HVAC system operates most of the year at partial capacity. Some systems probably never hit their design. And you can see over here in this little figure, this shows that there's a very small length of time that you have the design. You might operate at design condition, and most of the time you don't. Okay, so design engineer must design a system that will operate at high efficiency when operating at less than design load. Necessary to set up a series of control objectives and then design the control system to meet the objectives. To create a properly controlled system, we must establish control objectives, design a control system to be as simple as possible, i.e. as cheap as possible, to achieve control objectives. Control objectives must always be a realistic appraisal of the actual heating and cooling needs of the structure with economics of the project, the cost kept firmly in mind. Control system must be seen as an integrated unit with the action of one device affecting the operation of each and every other device in varying degrees. Okay, so establishment of a system flow rate will generally follow the basic load calculation on any particular design. So we use this equation, GPM is equal to Q, which is load that we're trying to satisfy, which would be a design load typically if we want to design flow, in BTUs per hour. And we're going to divide that by the density, and this is defined as pounds mass per gallon. So standard water is 8.34 pounds per gallon. H is specific heat, BTUs per pound mass per degree Fahrenheit, which in the US system is 1, unless the temperature goes up too high. Delta T is the temperature difference, the supply to return, and 60 converts the minutes in GPM and the hours in BTUs per hour of the load. So the density, 8.34 times 60 is 500, and so this becomes Q is equal to 500 GPM delta T for standard water. Okay, let's look at the direct return. We've talked about this, we introduced it before. After we've established the flow rates, the system must be designed that will permit this flow rate to occur to our varying zones. The choice of particular piping arrangement affects the flow rates that you're going to get in each circuit. So we're showing 7, say, offices or 7 different rooms that's going to be conditioned. Each one has a separate coil. We have a central circulating, our system pump. So assume a design that requires 7 coils, each on a separate circuit and each requiring 50 GPM. Piping the units with direct return will induce balance problems because, as we know, this first circuit over here has a short supply piping up to here. Then we go through the circuit and a short return. If you look at 7, we have to supply all the way down here through the circuit and then all the way back, which has a huge pressure drop. So if the coils all have about the same, it's going to be hard to push water all the way out to circuit 7. So direct return can be difficult to balance. The top figure here shows a typical pipe selection. And so we see that on the x-axis we have the required volumetric flow rate and GPM. And then this is head loss in feet of pressure loss per 100 feet of pipe. And then so we pick different diameter pipes. And this is for Schedule 40 black steel pipe. You can find these charts. You can find them where you look it up, or you can find computerized versions of this. But let's say we're looking at 1,000 GPM. So the biggest pipe would have, a 10-inch pipe would have almost no pressure loss, 0.5 foot per 100 foot of pipe. If we go up, then what, we're going to hit the 8-inch pipe, and it's going to have about 1.5, a little over 1.5. If we keep going up, we're going to hit the 6-inch pipe. What's that? That's about 6, if I'm reading it. No, it's about 5. I think that's about 5 foot, and we can go on up to 5-inch pipe, and that's going to be over 10. That's going to be about 13 or 14 feet. So you use this to, based on how much pressure loss you want to design into the system for your straight pipe. And then we have loss coefficients for the fittings for standard elbows and radius elbows and all that sort of thing. So that would be K times the velocity head, which would give you the feet of loss. So anyway, so we just work our way around the system to calculate what the pressure loss is going to be, and then select a pump accordingly. Okay, back more on direct return systems. Even though unit GPM requirements are the same, the circuit pressure drop differentials vary, as no two circuit lengths are identical. Direct return piping requires the installation of balance valves to even out the flow distribution. As the circuit length increases, the required pump head also increases, and the balance problems become worse because if you have more and more of these things, you have to have high pressure to force the flow to the furthest out coil or zone, and the ones close really become overwhelmed by that high pressure. So it's a problem. High pump head will require the balance valve on circuit number 1 to be almost closed. At this position, velocity through the reduced port area may be high enough to cause noise and damage the valve pretty quickly. The reverse return system, the 2-pipe reverse return, is generally preferred over direct return, as it provides a relatively even flow distribution. So this thing is pretty much self-balancing here, much more so. Now that's assuming that the coils are pretty much the same. If the coils vary a lot, then that's kind of a hitch in the get along here, and so this may not help out. But assuming that each of these coils has about the same pressure drop, this reverse return scheme, where we have short supply, but when we come out of the number 1, we go all the way down and back, this tends to equalize the pipe length for any of these. So, we have short supply, long return on 1. On 7, we have a long supply and a short return. So they tend to equal out, which makes it easier to balance. Let's see, if design requires varying flow rates through coils, say 50 GPM through 1, 90 GPM through 2, 30 GPM through 3, etc., designer should select internal coil circuiting that will produce equal coil pressure drops at the different flows. So even if the flows are different, we want the pressure drop across each coil to be about the same, and then the reverse return will equalize the piping distances and make it much easier to balance. So that's interesting to know. Multi-type arrangements sometimes, and we mentioned this also slightly previously, but so let's say that we have a 2-pipe reverse return on our distribution piping and direct return on the branch circuits. So here is my distribution piping coming out of my pump. And so, here to this first riser, we've got a short supply, but then we have reverse return to make these things relatively balanced. But, sometimes because it's hard to run the piping up and down on these vertical risers, they will be piped in direct return. So we see that up to here, over to the first coil and down is short. To the last coil, it's long on the supply and long on the return. So you know, if designed properly, this can work okay. This arrangement is found in apartment buildings, as the direct return arrangement simplifies riser piping, although two-pipe reverse return main distribution piping will tend to balance the system and establish good control. The smaller direct return riser circuits will tend to upset the overall balance. There are some guidelines here. In order to limit flow imbalance with this arrangement, the pressure drops of the individual circuits AB, A1, B1, or A2, B2 should not vary by more than 25%. So you want to keep basically the coils, that's primarily coils, a little bit of piping, to have pretty much the same pressure drop. And should be a high percentage of the total riser circuit pressure drop, which would be the pressure drop of AC plus the furthest most circuit AB plus BD on the return riser. This will serve to drive water flow out to the end, that last subcircuit, AB. The riser pressure drop of AC plus BD should generally not exceed 50% of the subcircuit pressure drop, which would be the pressure drop of AB, to obtain even flow distribution. Or the pressure drop of AB or A1, B1 or A2, B2 should be approximately twice that of the supply riser AC plus the return riser BD. So that's a little tedious, but if you follow those guidelines, they will help to make sure that we can distribute the flow properly. Okay, and I think I'm going to stop at this point, and I will post another video before long. So enjoy this one.